Hello, my name is Mariano Sanchez. Welcome to my presentation. This presentation is for English for Professionals and Academic Communication class. And today I'm going to be talking about the methodology for new design process for snap-fit joint designs in the additive manufacturing industry. So, first of all, I would like to establish two main things before I start, which are that the first one is that 3D printing technology is relatively new, and because it's relatively new, there's a lack of already existing procedures for it. The second thing I would like to say is that 3D printing presents one main problem, which is the limitations with regards to space. You cannot print something that is bigger than the 3D printer chamber. So after I've said this, the main objective of this presentation is to introduce a brand new way of creating snap fits or snap fit joints in this industry, which there's a lack of procedures, as I previously said. And to prove that this standardization is very, very useful and effective, I'm going to be using a case study of a gallon made out of plastic. So at first, it's important to mention the flaws of the already existing procedures of snap fit joints as a whole. The main problems is that the interlocking process or the gluing or the strategies that are made are not good enough. They're not precise enough, especially in hollow objects. They're not good enough. But not only that, but they also lack information about. They don't take into account many factors like the type of a structure that it's being used, and they also do not give information about other materials that might be needed during the assembly. So to present the proper way of doing a standardization procedure, I'm going to be using a guideline made out of 4 stages, which are performance condition, stage number 1, stage number 2, conceptual design, detail design, and design validation stage. So the first stage the performance condition consists on basically taking into account all the inputs of the production. So considering the type of 3D printer that's going to be used, and the thickness of the layers, the dimensions of the object, the geometry of the object, and also the type of assembly that we want. If we want to assemble it and disassemble it continuously, or we want it to be fixed. All these topics are going to be discussed in the first stage. The second stage, conceptual design, goes more into where to divide an overall structure to then 3D print it, where to locate the joint fits, like the snap fit joints, and which type to use. The third stage, detail design, focuses more on deformation, dimension, and material deformation limits, on deflection, dimensioning, and the retention force. All these areas are going to be covered in the third stage. The fourth stage, by the other hand, just validates the previous stages and gives the hands up for the final production of the structure that we want to create. So moving on, we're going to take a look into the case study, the gallon made out of plastic. And in this case study, based on the first stage, on how to divide it, on the conceptual design mixed with the performance condition design, it's possible to see that, or a conclusion came that there were 3 different ways of creating this bottle, which are divided in 2 parts, divided in 3 parts, or divided in 6 parts. So taking into account all the previous stages, especially stage number 1, number 2, and number 3, which are conceptual design, the 2 and 3rd are most important, conceptual design and detail design, it came to a conclusion that even though the third stage saved a lot of material, support material, and a lot of time to produce, it did not fulfill many of the areas that needed to be fulfilled. And we only know this because we took into account the other stages. So we came to the conclusion that even though it saved all this stuff, the third stage, it didn't perform well in detail stage. So the detail design stage. So the object was likely to deform, to break, it could malfunction. So it's possible how to see how the use of the stages is very, very useful. So the final conclusion is that the six-part division was the better option to take, since the validation state could validate that it was the best option. It was less likely to fail. It was better. The aesthetics were good. So the validation stage, which also includes the ergonomics, the force that you need to put an assembly in and out, all this kind of stuff, can be validated and are very useful. So to conclude this presentation, I would like to say that the experiment was effective, and this new procedure is brand new and could be very useful. Thanks for listening to this presentation, and goodbye.